Introducing myself, I guess, because I've not met all of you yet. I'm Emma. I work at the LSE in London with Lenny. And I guess he's been lecturing you for the last couple of days on methods such as the gradient descent approach to assimilation and why that works well when your model is not perfect. And so I guess what we want you to do today is to just get a bit of a hands-on feel for using this assimilation technique, the gradient descent method, and we're going to get you to do it using the Lorentz 63 system, for which there should be a piece of code that's available for you to download. So as soon as that's available, if you download that onto your machines and unzip it, and then just open it up, and we're going to start having a little bit of a play. And so there's a number of tasks for you on this tutorial sheet here that I guess we'll either try and work through together, or I'll leave you to work through it. Anyway, is that up now? So you guys can all find that gzip file okay? Yeah? So if you download that and then unzip it and then open MATLAB as normal. So I guess what we're trying to get you to do today is just have a play with the code and some of the parameters, and just fiddle around with things, see if you can get an idea of how these things work in a real model, in real life, I guess. And the system that we'll start with is simple Lorentz 63. So again, I guess at this point I should thank a guy called Du at the LSE who's made this code available to us. So we should be very grateful to him who's put it available to us. Basically just open it up, have a play, start running, see if you can run it. If you have problems running it, then I'll come by and help you. But all we want to basically do is try and make plots just to see what's coming out. Plot the observations if you can. I can come by and help you do that. Plot the trajectories, plot the results that come out of the gradient descent assimilation scheme. So just feel free to ask me any questions if you've forgotten what gradient descent is and how we go about the algorithm. If you forget what the Lorentz 63 equations look like, I can try and do my best. Is it not working? Is it not there? Has anyone managed to download it? And you've managed to unzip the file, and you've loaded it into MATLAB. Sorry? So if you need to download the whole file, the whole directory, and there should be a directory called gradient descent. Yeah? And so there's a lot of files with .m, and the main one that you're going to try and run is main.m, okay? So have you done that?
No, that is success.
No, it doesn't work. Right.
Now I got the problem. So what is the ULS here? Okay. So these are the.
So this tutorial sheet is available on the website as well. So if you manage to get it up and running, then just start working through some of the problems, and obviously I'll talk you through them as we go. So this is on the web page as well. It should be.
No, text read. Yes, text read will, because your loading is the problem.
So yeah, all of these files are things that you can run. So the main one is called main.m. So this is the one, this main.m is what you want to try and compile and run. So if you go into MATLAB, Yeah. The text where it saves text files, or you need to change the double quotes to single quotes where it's writing a text file. So, sorry, in two files. Yes, so that's in main.m and in gen_is. So there are two files. Let me come and help you. Well, I don't know what that is. So go back to main.
This is the main data.
And so which line was it on? As well, except I forget where Amit's put the tutorial sheet. He did put it online, didn't he? Yeah. '63 system. It starts off with the three equations for the Lorentz system. I don't know who's not familiar with Lorentz 63. Who knows the equations for Lorentz 63 that I can write on the board? So it's a simple system-ish. It has... I don't want to rub that out, do I? Sigma x y minus x.
Y dot is equals to Rx
Rx.
Simply Rx. You don't have to do that as Rx minus y minus xz.
Minus x z.
And z dot is equals to xy minus bz.
xy minus bz.
Where sigma b and r are the parameters.
Yep. So I don't know if can anyone see that. So you've got basically three dimensions to your equations. You've got an x, y, and a z, and it's basically solving these equations. You're generating some observations with noise, and then the gradient descent algorithm is finding the trajectories of that model. So what you should get at the end, I guess, so sigma and b are your parameters of the model that you can have a play with later on, not just yet, to see what happens. Is that okay? So what you should get out at the end is the resulting trajectory. So you should see a plot that comes up for each of these components, the x, y, and z, one of which is the truth that the model, so by generating these equations from a set of initial conditions that are also parameters in your model. Then you should see what comes out of the observations with some noise added on, and then you should see what comes out when you do the gradient descent algorithm at the result at the end having assimilated those noisy observations. And so there should be three different plots with those three lines on it. You should see that they're all pretty similar. Is that what everyone's getting? I see some nods. Anyone else? Great. Huh? Do I have the graph on my machine? I could, but I can't connect the machine up. That was the problem. We can either have the tutorial sheet up or the graph. Yeah. Okay. Oh, I'm in the tutorial sheet.
It's not working. The problem in this.
Okay. So do you want to turn that around and I'll... So go back into main for me. Where's line 22? Which, you're using MATLAB, right? Go back to the error message again. What does it say? Undefined function. And you have, there is a generate model states file in... descending model states. Not working straight away. But the next thing we want you to do, once you've had a look at the plot and you've familiarized yourself with the kinds of things that come out, so you've seen what the observations look like given the model, you've seen what the truth should look like, which basically in this situation in Laurent 63 we're using a perfect model situation, so that the observations and the results, the states from the model are being generated by the same model, basically. So what we'll have a play with later is what happens when your model is imperfect, and that's where this gradient descent method really comes into its own and really has something good to offer. But once you've familiarized yourself with that, what we then want you to have a look at is trying to plot and have a look at one of the fundamental parts of the gradient descent algorithm. So this is known as the mismatch. So I don't remember if you remember Lenny talking about it yesterday. So one of the things that we try and minimize when you're doing gradient descent is this thing called a mismatch. And again, I can't remember exactly the function that it is. But so you're trying to minimize something which looks like f of u minus, what was it, u. This is where I should get it right. of u. Is that right?
I plus 1.
Yeah, and I plus 1. That's right, isn't it? And so you're trying to minimize a function that looks like that squared. So what I want you to do is have a look through the piece of code. There should be in the gradient descent algorithm itself, there should be some numbers either called mismatch or I think it's called delta RS. Try and plot those numbers out and try and I think actually it generates an output file with those numbers in. And have a look over time, so before the gradient descent algorithm goes into the process, have a look at what the mismatches are. So this difference between your generated states, noisy observations, and the next step of noisy observations. Have a look at those mismatches, and then have a look at them after the gradient descent method and algorithm has happened. And then we'll get you to fiddle around with some parameters and see if you can either optimize or break the whole algorithm by playing around. Does that make sense? Does anyone? Sure. So I mean, you can fiddle around with the parameters and you can make the observations more or less noisy. There's a particular, I think it's just a random number generator, just to add some noise on. And so that's one of the things that we'll get you to have a look at later, is just by playing around with parameters such as the noise level, you can really see the difference between the original observations and the fact that it still finds a trajectory that's near the model, or as close to the model trajectory, even if you've got really noisy observations. And we'll show you that later on that also happens when you've got a model that's not perfect either. And so we'll show you how to do that. Who's still stuck? So you get 3 plots come up on the screen, is that right?
First one is for the state. Second, figure 2 is for the noisy observation.
For the
And the third one, the IS orbit is for the resulting trajectory.
so which one?
But the mismatch is being mostly paid for the noisy observations. Are this
Okay.
the mismatch?
So the three lines on that plot. So you've got figure 1, 2, and 3. Figure 1 is the solving the equations for x, basically. So the 3 lines, one of them, and you should be able to see. So if you go into main in the MATLAB code, one of them should be blue or B for blue, and then it tells you whether that's the true state or the observations.
Figure 1 is for
So figure 1 is solving the equations for x, or x dot, x bar. And so then figure 2 is for the y dot. No, so figure 1 contains all 3. It contains the observations, the truth, and the result of the gradient descent technique. So if you look at where in the main where it says plot.
Yeah, but how do you know which one is the true, which one is observed?
So
They were there, but then it's just naturally no one is differing.
So the blue one is, so if you go into the main .m, where it says, so true orbit here, so the red one is the truth, what's generated.
Oh, this is red, blue, green.
Yes, yeah. That might have helped to explain right there.
Mismatch is with the observation.
Yes. So the mismatch, you're using the observations, you're using the noisy observations and one step ahead.
Spikes.
2 seconds. Go on.
This is true state, this is observed state.
So this is so that is the result from the gradient descent algorithm. So you take the observations, you sort of propagate them forwards. So you then forget about the observations, and then you try and do the gradient descent technique down onto a trajectory. And so this is after the whole process. This IS orbit is the result. That's what it gives you, and you can see. So if you go back, so I guess the green and blue. So truth is red and green is blue. So blue is your noisy observations.
R is true. So observation and intermediate state, these two are pretty clear. These two are pretty close.
Exactly. So that's saying that your gradient descent algorithm is doing a good job, right?
No, but this is different from the observation.
So what you're trying to do is generate a trajectory of the model in this situation. So you've got your observations. So the only thing you have are observations, right? And then they're noisy. They have some noise on them.
Red and green are close together.
Yes.
So
That's what we want.
gradient descent and the true orbit are close together.
Yes.
And they're different from the observation.
Different from the observations. So you have observations with noise, and that's all you have, and you have some model, and it just so happens in this case your model is perfect. So the observations and the model states have been generated by the same model. Okay. So you've got noise on your observations, and you take those and you start trying to go through the gradient descent technique. You then throw them away and you say, okay, well, what I want is a trajectory which is a trajectory of the model. And so you want the green line and the red line, the truth, which is the model in this case, and you want the assimilated trajectory, the gradient descent trajectory, to be as close as possible, which, I mean, you can see is perfect there. So the blue one, the observation, is just something, a starting point, which you take them.
The noise in the observation is being filtered out in the whole process.
Yeah, and so basically what you're doing is you're coming towards the trajectory of the model. So we'll get you in a minute to try and fiddle around with the parameters, like take the noise level up and take it down, and see if you have, so the noisier the observations or the less noisy the observations, how much better or worse you do getting the green line and the red line to come close together.
Suppose you are saying it as noise. The observation, that the kinks in the observation, you are considering them as noise.
Well, so
But suppose we have a data set which this is the observation.
those are the observations.
In a kind of thing, you're smoothing out the whole thing, is it?
Yeah, sort of. So like, if you have a model, you have some underlying set of physical processes or processes that you think underlies your observations. When you make an observation, there's error on it, right? So it's not going to be a smooth function. It's going to have to be.
No, but sometimes the kinks are important.
Yeah, of course. Oh, no, of course. And so if the model also predicts those kinks, then you want
The
it.
model is not capturing those kinks. What generally happens is that
Well, then you come to this situation, which we'll talk about later, where you don't have a perfect model. So your observations, that you might well have the kinks, which are really important.
yeah.
But the model that you use to generate the states,
But this doesn't know that.
this doesn't know that.
This
But
doesn't know that it's a perfect model at the background.
it doesn't
It's
know.
observation and tries to.
And so what I'm saying to you is, so if we had a situation where the model also reproduced those kinks because the model knew that they were important, then the gradient descent algorithm would relax, would come down onto that trajectory with the kinks. It's only because this model. So we'll try and show you that later on. So that's one of the next things. Yeah.
Both the loops are using the same variable I.
Sorry.
Both the loops
Yeah.
are using the same variable I.
Ah, okay. Yeah. So just change it to J.
So which all will
So change that to J and change number of so that will be, these three would be J,
and rest?
and the rest should be I.
Register file.
Yeah.
What this J underscore SI is doing?
So the gen underscore, so that subroutine is the one that does the gradient descent algorithm. So what you would do first is you give it your model basically. So that's these three equations here. Now obviously you can start with a set of initial conditions, which is in the main.matlab code, and then you can generate the set of trajectories for that model, which are basically perfect. This is, given these set of initial conditions, you can sort of run the model forwards, and that gives you your sets of predictions, or your sets of futures, states. So then what you would do is, okay, well, this is my model, but I need to now generate some observations. Pretend I don't have the perfect model or the perfect observation. So I've got some new observations, and I want to assimilate those into the model. So I take them, and it just so happens in this case that the observations are generated by the same model that our predictions or our states are being generated from. And so we've just added some noise term onto that. So you've got the model states, or the truth as it were. You've got noisy observations, and what you want to do is you want to take those observations and include them in the model in a way that then makes the models, those observations from the model, relax onto a trajectory which is the same as the model trajectory. Does that make sense? So you want to minimize in a way that difference between what the two things are doing, and you do that by minimizing this mismatch function from observations or states and the state I+1. And so it goes through that process several times, and then in the end you end up with a mismatch which has been minimized to a level that's acceptable, and you get, I don't know, have you seen the graph yet? You've seen the three figures. So you can see on those figures that actually the green line and the red line are really close together.
Green and close.
So the blue ones are the observations that you start with.
Yeah.
Is that right? Yeah. So those are the observations you start with. They're noisy, but you want to put them in your model, and you want to get a trajectory of the model based on those observations. And so then the red line, I think, is what you get at the end of the assimilation process, and the green line is what truth should be. So you can see that they are, it's doing a really good job.
Red line is for the noisy observations.
Sorry?
Red line is for the noisy.
No, the blue line, I think, is for the noisy observations.
Noisy line will be
You can, so what you could try and do, I mean, I think that's in the tutorial, but later on what you can try and do is increase the level of noise.
that will be better.
Actually, for plotting them for each time step, we have to change time size.
So some of the things where are you, have you done the mismatch? So one of the things we're going to get you to do later is, yeah. So this is time in terms of, this is the number of observations. So for your 100 and however many observations that you choose, time step 1, time step 2, that graph shows time scale in terms of, those are the observations that you're taking over time. Does that make sense?
If the noise level is increased, that is, the observation is further away from the model state, that is, in order
It might be.
then in order to come to the true state, does it go through more iterations and hence more time?
It might take a bit longer, yes. So what you're trying to, so you minimize this, it's kind of small on the board, you minimize the mismatch function, and it will just keep going through the loop until it gets to that stage. So if they're really noisy observations, actually what you find is it might never get there. So you would set an upper limit of the amount of time you try, or you would reduce, you'd say I'd be a bit more relaxed about how close I really want them to be. Does that make sense? Right, wait, here first. Sorry, let me come up because I can't hear. Say that again.
Is there any reason to take number of states and they 2 to the power something?
So is the 2 to the power?
Your number of states are 2 to the power 40 something.
Yes, yeah, we just wanted a large number of them. I think.
It's random.
So that's another thing that you can have a play around with. You can start changing those numbers to have a look.
In this generate model states .m, you use same Ratikutta method twice.
We use the same, so we're using, in this case, it's the perfect model situation. So you're using the same model to generate the observations as you do to generate the model states.
In first state, you predicted the initial condition, and then you find like this.
Yeah. So what we will do later on, maybe in the next tutorial or maybe today, is we'll let you play around with the model that you generate the observations from, and we say you can have a slightly different model with the observations and generating the model states. And you can see that actually the gradient descent method really comes into its own. It really still does quite well. Obviously, I mean, you can't have two completely different models because it would never work. But if you've got some structural error in your model, that this is when this method really works. Okay, does that make sense? And we'll allow you to play with some of those later, and I'll show you how you can do that a little bit later. Okay, is that okay? So is everybody now okay with the first 2 points? So everyone's run the model and got some graphs out? Anyone not? Do you want to put your hand up if you haven't? Or just signal me later on and I can come around and help you get it running. And so part B is obviously just then looking at the figures that come out and making sure you're familiar with the fact that, so you've got the 3 figures. One is for solving the equations in X, one is for solving them in Y, one is for solving them in Z. And then you've got the 3 lines, one of which is noisy observations that you start with, the other is the truth from you running the model forward, and the other one is the assimilated, like from the gradient descent assimilation, what the result should be. And actually you see that the truth and the result from gradient descent is pretty close. So what I want you to do then is to have a look at this mismatch function, the thing that you have to minimize for the gradient descent technique. And I think that should be in a function from the main file of something like, what is it, generate is, genis.m. There should be some stuff in there which then gives you the mismatches between the observed state and the observed state plus 1. So what I want you to do is print those numbers out. I think they're already printed out from the code actually, but try and plot them and have a look and see how you think at the beginning, before the gradient descent process starts happening, and afterwards, just to see how those mismatches change. So I was supposed to tell you as well, everybody, that Chris said that we need to be back here at 5, so you're free to go off and have tea and coffee and stuff whenever you like, but come back for 5 and we'll finish up and we'll discuss how far you've got. So which one? Yeah. So we have a time step in terms of, you're looking at 128, I believe, observations. So you're generating 128 observations. Yeah. Well, so that you're generating 128 model states. So you're stepping forward in time. There's a time associated with or time scale associated with the minimization algorithm as well, which is the window length, and we can try and vary that a bit later.
100 observations for 100 different times.
Yes, yeah. So you're basically stepping. So you solve this equation. You say, okay, well, so my next x is, the last x. So for the next observation, basically, the next time. Yeah. I guess, yeah. Basically, the next observation time is used as the next one. You okay?
Stop this program and gave a noise level of 5. It's going on eternally. Can I stop it?
You can stop it. You can just press a Control C, or you could just wait until it finishes. Sorry. So you've changed noise level to 5.
Yeah, I want to see how it happens.
Well, so you said it took quite a long time. Yeah, we'll leave it for a little while and see. Or maybe you could try something like 2 to start off with.
Oh, very interesting.
Is it because your laptop's not plugged in, you need some battery? So has anyone managed to plot the mismatches yet? No? Have you managed to get yours running yet?
Yeah.
Yes. Great.
Do you want to change it?
Well, no, not 5%, as in try go.
From 1 to 10, running like for 5 minutes.
I think.
Should we decrease the mismatch? Because the number of items will change. I don't know why it has nines.
So that's, I think, something I will look at the next time. A couple of people have said change that parameter. Yeah, okay, great. So if I can squeeze through, sorry. So you guys struggling with something? Yeah. Sure? You have a question? No? Yeah, okay. Great. They're having a play with initial conditions. You tried changing those? Yeah, so I guess what I'd like you to do is just to have a play in general, like change the noise levels, see what happens, try and change the size of the simulation window, even maybe that doesn't work quite well yet, so I'll check that for next time. Change the initial conditions and see what happens, and then just have a play, maybe make some plots up for next time, and we can have a discussion about the kinds of things that are going on. You know, what happens when we increase the noise? Is it better to have a longer, shorter assimilation window? So we can start having a play with that. And then next time, what we're going to do is show you how the assimilation scheme works when the model isn't perfect. So what we'll get you to do is actually change some of the structures of the models. Maybe we'll divide you into half of the room and another half of the room, and give some of you one type of structural error, another half of you some different type of structural error, so that you're not taking the observations that you generate from the same model as you generate the system, the model states from. And we can see how the gradient descent algorithm works in that case, and again have a play with the parameters. And so I think that's where you'll really start to see where this technique kind of comes into its own, where it's actually really very good. But yeah, just let me know if you've got any problems doing the first few bits for now.
Is true minus observed.
True minus observed, so the truth minus the observations, okay.
And
So that gives you some, I guess, indication of what the noise on the realization, yes.
after the gradient descent.
So after the gradient descent, so you plotted gradient descent minus the truth. True minus the gradient descent. Like also, I think that's, I think that's fine. Yeah, I think that's fine. I mean, so all that's saying is that your observations were noisy, and in the end, yeah. So I think that's fine.
But we have not plotted it. Actually, that will just.
Sorry? So this initial state, you can change the initial conditions. So you just change X, Y, and Z in the code and see. Yeah, just choose what you like and see what happens. You okay there?
What you are doing with this GD.m?
Yeah. So which part are we in here? We're in...
This you call somewhere to find the gradient descent.
Yes. So which subroutine is this, sorry?
Yeah.
So this is...
In this subroutine, this will be somewhere.
So you see, so this delta here is the mismatch function, the thing that you're trying to minimize, right?
Okay.
So you take that function, and then you pass it through the sort of gradient descent algorithm so that it minimizes that function, and all it does is roll down onto it.
I required this mathematical details, so that means it's easy to find out what are the steps.
So there are a couple of papers which actually I could send. Yeah. Yeah, so we'll send the papers around, and we will discuss I think actually Lenny's lectures are over now, and I guess we would have liked to go into a bit more detail. So maybe next time at the beginning we'll go through the algorithm a little bit.
Because finding the details from the code is slightly difficult.
Yes, it is. I agree with you there. So I mean, the essential thing is this mismatch function. So you take the mismatch between your observations and then where your model trajectory is moving to, and you take that mismatch and you minimize that down. And the minimization is a standard mathematical procedure, basically. And so that would then call this. Where is it?
Somewhere I checked that you use this GD function.
Yeah, so the GD function is the real, again, the core of the actually minimizing.
Here you use this. Okay, then find some modify value, and then again you continue this.
Exactly, you keep going down and down and down until you find that that mismatch number is at a level that you're satisfied with. You say that's okay, that's good enough. And you choose what good enough is for the purpose that, you know, whatever you're looking at. Is that okay? So yeah, I think I'll send some papers round about
Yes.
with a little bit more detail. Maybe next time before we start, we'll go through some of the real basics again of the method. So today I just wanted you to have a play, see what you can find out for yourselves, and then we'll discuss it next time. Okay?
Same model you discussed derived from so many places. I checked.
Which one? Sorry.
Same model, same
Yeah.
model you define in so many places. I checked.
So I think it's defined, so it's in 2 places, and there's a reason for that. One of them actually isn't being used at the moment.
Okay, one
So-
is for model equations.
And the other one is system equations. So next time what we're going to do is look at what happens when the model isn't perfect. So at the moment your observations and the model states are being generated by the same set of equations. So what happens if actually we don't have the right model, and which is like the case in most of reality. We don't have the right model. I mean, you know, we don't know the exact parameter values, or something is missing from the model. So next time what we're going to do is give you that some kind of structural error or parameter uncertainty in the model, and we're going to see how our method does. So next time. But yeah. So are we supposed to finish now, Amit?
Yeah, soon. I mean, it's about 15 minutes.
Third one. Step size we have to change?
Yes, step size. Hopefully that works okay.
When we are changing the step size from 0.01 to 0.001, so it's coming something like sinusoidal curve.
Okay.
And when we further reduce that, then again it's becoming very bad.
Okay, so let's have a look. So, which one's step size to start? Yeah.
Yeah, it may come still in time, but
So what does this show? This is observations. I forget which. So the red one is the perfect, is the truth, and the green one is what gradient descent gives you. So it's not too bad. It's still a little far away. So
it's error is somewhere over here, but here it's fine.
So that's choosing a really short window.
But when we are changing it to some other one, so suppose we are reducing it further, then it changes.
So you changed it from what originally?
It was 0.001, so
Yep.
that was giving a fine.
That gave the original plots, right? Oh, what's that? That's funny, isn't it? Wow. So I guess the noise is quite high for that level of step size. I think that's what it's telling us. But I mean, yeah, maybe you don't do great, but you don't do too badly. So I guess what you're trying to, one of the things you try to do is by changing some of those parameters, by looking at different window lengths, window sizes, you're trying to find out, you know, what is better. I would use that word optimal, but Lenny really doesn't like it. So what's better in this particular case?
Step size is actually determining what all data we are taking from the true one.
Sure. yeah, if you take too short a window to try and generate the information, then I don't know. So if you increase it as well, that goes bad again, or just
No, originally it was 0.01. So if I decrease by
yep.
so now the error is less.
So it was 0.01 to start off with, and that gave you the original curve. 0.001 goes a bit better.
Yeah, it's a kind of sinusoidal. And when I'm reducing it further.
But what did the mismatch look like? What is the distance between?
The mismatch is almost the same in the three cases because it's around of the order of 10 to the minus 3 in the final.
Yeah, I guess you tell it what to end up at, don't you? So, but so how, compared to the 0.001 case and the 0.01 case, how much does the green line and the red line?
Yeah, that is it.
So you say that the smaller is better?
No, not the smaller. For 0.001 case, it's better.
So try increasing it and see actually if you get even better. So it might just be that I think that there's an optimum length, or there's a better length of window to use for, and that is generally longer. So has everyone been happy playing with their codes now? Everyone managed to get it working and have a play and have a little see what's going on? Is to look at what happens when the model is imperfect. So when you don't have the right model, when the model that you have to generate your observations is not the same as the model that you have to generate your model states. And so that might give us quite a nice insight into the strengths of this whole approach. But yeah, next time. Carry on.